Okay, so this work was done over a number of years with various co-workers. So in my group, Kati Stadler was a PhD student who recently graduated about a year ago, and then work was continued by Elias Walter, another PhD student. Seung-Sup Lee, who is also here in Aspen today, joined us in this latter part of the project. The numerics was spearheaded by Andreas Weichselbaum, who's responsible for all our NRG abilities. And it was initiated by Gabi Kotliar about 7 years ago when we had a very fruitful discussion. And his postdoc Yilin Wang also joined during the last parts of the work. And so several publications have appeared. I will briefly go through some of the results of the first few, but my main goal is to focus on the last two. And thanks to the very extensive introduction of the previous two speakers, I can keep my introduction very brief. So the topic are Hund's-metals. Those are multi-orbital systems where Hund's coupling plays an important role, and they're correlated. But these correlations are driven strongly by the Hund's coupling and not only by the Hubbard U. In fact, even if the Hubbard U is quite small, you can get strong correlations. And the fact that the Hund's coupling plays an important role means there's a non-trivial interplay between orbital and spin degrees of freedom. And even if the orbital degrees of freedom are all degenerate, as one can study in a model Hamiltonian setting, then 3 bands are actually different from 1. This is a phrase that I took from this paper by Philipp Werner and company, who were among the earliest ones to focus on this type of physics. And Jani discussed their contribution in his talk. Okay, so we will be interested in elucidating this interplay between orbital and spin degrees of freedom. Another key property is these are bad metals at large temperature, so there's incoherent transport. But at very low scales, there's a crossover to Fermi-liquid behavior. And it was also in the previous talk emphasized why or how this very low Fermi-liquid scale comes about. So the collective name for all these properties by now is Hund's-metals, right? This phrase, I believe, first was used in this paper here. Okay, so the questions that I will address in my talk is first, there's this coherence-incoherence crossover as a function of temperature. What is the nature of this crossover? What are the energy scales involved? And then in many DMFT computations, there are what looks like power law behavior in intermediate energy scales. And my main goal is to try to understand where these come from. And to do that, it will turn out to be useful to modify the model description in such a way that you can tune the Fermi-liquid scale to be very small. So similar in spirit to what was said at the end of the previous talk, I will raise the question, can we actually tune this Fermi-liquid scale to 0 and what happens then? Okay, and my strategy will be not to try to do ab initio calculations, but to the contrary, to use minimal models that one believes still contain essential ingredients of the physics that matters here, and then detune them from the regime which come out if you do DMFT, for example, but where the energy scales are not very well separated into a regime where you, which you might call unphysical, but which helps you to clarify what's going on. Okay, so the minimal model that I will be using has been studied by a number of people before us. It basically is a 3-band Hubbard model with Hund's coupling. So you have 3 bands on a lattice, 3 orbitals on a lattice, and a Coulomb interaction with Arbeit-U, and then there's a Hund's coupling, which favors alignment of spins on the same atom. And I will study this at an occupancy of 2, average occupancy of 2. So that means these 2 spins on the site want to align. 2 is important because 1 away from half filling, and that's relevant for many of these materials. And that means in particular there's 1 orbital degree of freedom, namely where is the hole on the site. And this can sit on any of the 3 levels, so there's hole dynamics or orbital dynamics. And then we treat this using DMFT, so we neglect momentum dependence of the self-energy using beta lattice. And this is then mapped onto a self-consistent Anderson-Hund model. So an impurity model, which you have to solve self-consistently coupling to the band. Under these conditions, N equals to 2. And we treat this with a numerical renormalization group. So let me just very briefly say a few words about this method. So it's an impurity solver that gives you real frequency results. And well, for this, for today's purpose, we need it to be able to solve 3 bands at very low temperatures. So the fact that one can deal with 3 bands is due to technical advances made in the last 2 years by Andreas Weichselbaum, who managed to set up a very powerful tensor library that allows one to treat non-abelian symmetries. And without that, we would not be able to do this work. Yeah, but the key advantages of this method for our purposes, it gives real frequency data at arbitrary low temperatures. All right, and as you see, I listed some of the technical papers here. Andreas's role is essential there, so he really deserves a lot of credit. Okay, so having decided to study this model, it might be useful if I just give you a short overview of the phase diagram at 0 temperature as a function of U, Arbeit-U, and here the Hund's coupling J. And so there are 2 critical lines here. So on the left, system is metallic. On the right, it's insulating. And here in between, there's a coexistence region as usual. And what we're all used to from the Mott transition is at 0 J, if you increase U, you will eventually get to a Mott transition. And to illustrate what happens, for example, if I put the parameters right here at this brown star and you compute the local spectral function as a function of frequency, you see something like this. So the blue curve is 0 temperature. And so you get a quasi-particle peak, but as you lower the temperature, this gets suppressed, you get a pseudo gap eventually, and so you're very close to Mott transition. And if you move across here, you'll get the typical Mott system. Now, if you instead turn on J, so you put yourself, let's say here, J equals to 1, small value of U, then the spectral function looks like this, again as a function of the 5 temperatures shown down here. So in this case, there's no Mott transition. As you lower the temperature, this quasi-particle peak does get suppressed, but it never turns into pseudo gap. And the shape of this quasi-particle peak at 0 temperature actually is a 2-tiered structure. So there's sort of a broad bump. If you look at the blue curve, I just highlighted it by hand, and then followed by a sharp needle. And these 2 structures we interpret as a orbital condor peak due to screening of the orbital degrees of freedom and a spin condor peak. This was also alluded to at the end of the previous talk. And the fact that they have different widths is the first indication that there are 2 different energy scales at play here. And then you can also get some combination or some mixture of these 2 if you put yourself here, so finite J, but closer, larger values of U, get a structure like this. So you again see this sort of 2-tier structure here. But if you increase if you increase temperature, the quasi-particle peak gets suppressed quite strongly. So basically what I want to say is there's sort of a smooth continuum of behavior as you tune parameters. But if you add large J or a finite J and small u, the behavior is quite different from what you are here. And so this regime here is what I would like to call a typical Hund physics. And in this paper over here, done together with Gabi, we argued that strontium ruthenate is actually falls into this regime, whereas a typical example of this one would be vanadium oxide. All right, now having talked about these two energy scales that one can sort of intuit from this two-peak structure, one can nail them down more precisely from spin and orbital susceptibilities, as I will discuss next. But let me just point out, if you plot those here, so the dashed line is the orbital condor scale and the solid line is spin condor scale as a function of u on the same scale as here, you see that as you decrease u, there's a window, quite a big window that opens up between these two scales. So in this window here, spin orbital separation happens, as I will elucidate. And as you increase u, this window becomes smaller. But and I should also mention this window only is open if you have finite values of J, right? So the question would be, what is the physics in this regime? All right, so let me follow up by discussing the spin orbital separation in terms of behavior of the spin and orbital susceptibilities, which you get by basically calculating spin-spin correlation functions, the function of frequency, or orbital-orbital ones. So just to set the scales, in the top plot this inset here, that is one of those finite J systems that I showed you previously, the spectral function. And now with NRG, one can zoom into very low energy. So I can plot this on a logarithmic scale. The fat solid line shows the negative frequency branch, and the thin line, the positive frequency branch. And so this two-tier structure becomes clear very directly on this logarithmic scale. And then below, on the same scale, I plot the spin and orbital susceptibilities. The solid line is the spin susceptibility, imaginary part of that. And then as a peak, at the position of the peak, that we call the spin condor temperature. And then the orbital susceptibility is this dashed line, also has a peak, but at a somewhat larger scale. So the fact that spin screening here occurs at much lower scales than orbital screening, that's what we call spin orbital separation. And intuitively, the way to think of it, at large energies, these two spins per site are bound into total spin of 1. And then when orbital screening happens, the system binds one extra electron from the conduction band to screen this whole degree of freedom. And you can do it in such a way that the total spin becomes spin equals to 3½ and so this spin then still interacts with the conduction band and at the spin screening scale, it's bound into a total spin and orbital singlet. And I will elaborate this process more later on. All right, I should just mention, so this regime of spin orbital separation is what was called spin freezing by Philip Werner and his colleagues in 2008. And the way I understand it, the reason for this name was that since the spin screening scale is very small, the spin dynamics seems to slow down a lot. And the slowing down of the spin dynamics is why they use this phrase spin freezing. So the way I like to think of it is, in this regime, you have screened orbital degrees of freedom and your spins are still unscreened. They fluctuate quite freely, but there's still some remnant effect of the orbital degrees of freedom left. Okay, so my next goal is to try to understand what happens in the spin orbital regime, the spin orbital separation regime in more detail, because it turns out in this regime there, in various calculations, seem to be apparent power laws, and the question is, can one elucidate those better? Okay, so this is one of the places where my slides take a lot of time to flip. So let's see. I think right now my presentation is taking some time to flip over for reasons that I couldn't figure out. So maybe are there questions on what I've said so far?
Christian, why don't you come up right here? So there's one question by Christian.
Okay. Can you do you understand where the asymmetry of the spectral function come from? I mean, it seems that you have the asymmetry on the side on the below the Fermi level when n is 2, and I guess above the Fermi level when n is 4, isn't it? But why it's asymmetric? Why you would naively would expect that maybe this needle will show up on both sides? Why it's only on one side? Do you understand?
I don't have a detailed understanding, but I mean, the fact that the model is particularly asymmetric, for that indicates that I should not expect the spectral function to be symmetric either. So I just have that very qualitative statement. So I've not tried to figure out in precise detail why it looks the way it does look. But I mean, you have two particles in a site which can host 3 electrons. So it's plausible to me that things should be asymmetric.
No, it should be asymmetric. The question is, why is needle on one side?
Okay, so I don't have a direct answer to that. So I didn't try to understand in detail why it looks like that, to be honest. Okay, so my slide managed to switch, so let's continue. So to try to elucidate this behavior in the spin orbital separation regime, the idea will be as follows. Let's give up on DMFT self-consistency. Instead, let's just consider the 3-orbital Anderson-Hund model, that the impurity model that underlies this DMFT calculation, but not solve it self-consistently. So this is my cartoon for that. You have 2 electrons on 3 levels, hybridizing with 3 conduction band, 3 degenerate conduction bands. And this shows orbital overscreening, because you have this has a non-Fermi liquid regime, but the Fermi liquid ground set, because the spin Kondo scale is not 0. And then one can follow an idea that Gabi and Camille Aron had a few years ago, and that was also mentioned in the previous talk. You go to the, you consider the spin orbital Kondo model that you get if you do a Schrieffer-Wulff transformation. So now in the spin orbital Kondo model, you no longer have direct hybridization. You instead have 3 exchange coupling constants, spin exchange, orbital exchange, and a mixed one. And these 3 parameters are bound together by the Schrieffer-Wulff transformation. But you can now take the point of view, let's choose them independently and tune them in such a way that the spin Kondo scale goes to 0. And then you get a large regime between the orbital Kondo scale and 0, in which non-Fermi liquid behavior, if present, can be elucidated in a lot of detail. And then we will do this using both NRG and conformal field theory in the spirit of Affleck-Ludwig. Okay, so the 3-channel spin orbital Kondo model has the following structure. You have a conduction band, then there's an exchange interaction between the local spin and the spin density at the impurity site with coupling constant J0. Similar term in the orbital sector with coupling constant K0, and then a mixed term where both the spin and orbital degrees of freedom couple to the lead. And the model has U1 times SU2 times SU3 symmetry, because we treat all the bands to be degenerate. And now the Pullman scaling flow equations for this were worked out by Gabi and Camille Aron. And I show you qualitatively what it looks like here. For a fixed value of K0, if you plot the flow as a function of J, so the spin exchange coupling and the orbital exchange coupling. And if you put, this should be J0, sorry, and I0. If you put J0 and I0 to 0 and just keep a finite orbital exchange, you get this black line. You flow here to a non-Fermi liquid fixed point. But if you tune these couplings to be non-zero, so the spin exchange or the mixed exchange, then you flow away from this non-Fermi liquid fixed point to some Fermi liquid fixed point. Okay, so what that tells us, if you want to study the behavior of this fixed point, we should keep these guys very small or zero. And that's what we will be doing in what follows. And let me indicate down here how these spin susceptibilities and orbital susceptibilities behave. So if you take an RG trajectory like this, where the spin exchange is quite large, then you get the type of plots that I showed you earlier. So there's a orbital condor screening and then spin condor screening. And the regime of spin orbital separation here is not very big. But then if you tune J0 to be smaller, you get here, you can push apart these two scales. And as you keep making J0 smaller and smaller, this regime widens and widens until in the end, you can get it extremely wide. So the fact that it extends here over 9 orders of magnitude, that's a typical NRG situation where it's completely unphysical to make it this, to go over 9 orders of magnitude. But if you're interested in the mathematical properties of the model, it's very convenient to have so many orders of magnitude available. Okay, so in what follows, I will study this type of setting, or this one where the spin exchange is very small, and see what happens. And now to explain.
About 2 minutes.
2 minutes.
Yeah.
All right. So then let me just be very brief. I wanted to explain how the NRG strategy works. You take your system, you discretize the leads logarithmically, you map it onto a chain, and this chain can, where the coupling constants decay exponentially. Then you can diagonalize this chain iteratively by adding one side at a time. You have to truncate states, rescale, add another side, and in this case, in this way, you build up a many-body spectrum that's more and more finely resolved at lower and lower energies. And if you plot these rescaled energies as a function of iteration number, you get a flow diagram, which shows how these energy levels flow and how the system, the lower-lying states change its structure as you go from a small system to a large system with a very small level spacing. And this is what comes out in this type of plot. And now it might look like a complete spaghetti, but every colored line has quantum numbers that we know very well. And the level of flow that you see here is related to the behavior of the spin and orbital susceptibilities that are plotted down here. And first you see there's a large energy window between the orbital and the spin condor scales. The flow traverses a fixed point over here, just below the orbital. And then there's another scale where the levels begin to change. And as I mentioned, one can attach quantum numbers to all these levels and allow that to analyze what's going on. So at large energies, the ground state is simply the spin 1 free impurity. Then as you go below the orbital scale, you get spin orbital screening. And so this spin 1 object binds 1 electron from the band to screen the hole. And you can do this in 2 ways, either by building a spin 3½ or a spin 1½ state. Those are these 2 lines, but they're more or less degenerate. And then as you load energy even more, some splitting shows up between these 2, and the spin 3½ state wins. And in the end, it's screened all the way to get the fermi-liquid ground state. Okay, so one understands in detail what's going on as you lower energies. And now, interestingly, these spin and orbital susceptibilities follow well-defined power laws in this regime, very strange power laws with weird exponents. And it turns out one can understand all of these exponents by referring to methods of Affleck-Ludwig. If I had like 5 more minutes, I would explain that in more detail, but let me just flip through it. The general argument is each of these energy levels is associated as a specific energy which is associated with a boundary operator at the fixed point, which has a well-defined scaling dimension, which you can compute. And from these boundary operator scaling dimensions, by using very simple scaling arguments, one can rationalize all these exponents. And now, so what does this have to do with the real world? Well, in the real world, we certainly don't have so many orders of magnitude, but even in the data that I showed you earlier in the 2015 work, where you take the self-consistent Anderson model, one finds this exponent in the spin orbital separation regime. So my take is there is some non-family liquid fixed point hidden behind the self-consistent Anderson impurity model. You're not very close to it, but you do somehow sense its vicinity. So I should stop, right?
Yes, we're out of time.
All right. So in my last slide, I just wanted to give credit, or next to last one, to Jane, who did a very similar analysis, or had a similar idea of tuning open these scales. So he had these slides also. And then let me just end with pointing out one can take the idea of studying this three-channel spin orbital condom model in its own right even more systematically and plot a phase diagram. And the point that I just discussed here sits right in the middle. The physical regime is here. These regimes are not accessible if you study the self-consistent Anderson model, but the actual system is somehow is proximate to a non-family liquid state. And in that sense, that might be some indication for why one sometimes sees these non-family liquid power laws in other quantities. So with that, let me end.
All right, thank you very much. And we'll immediately go over to Antoine, who has a couple questions. Antoine, are you in a room with a microphone? If not, I will promote you to panelist so that you can speak yourself.
Can you guys hear me?
Yes.
Okay, thank you so much. Yes. So, very beautiful talk, Jan. I have the following question. So, in the early days of Hund's metals, in particular in the pioneering paper of Philip, yourself, and Andy, the spin freezing regime was characterized by square root of omega power laws in the self-energy. And so my question to Jan is, can one, with hindsight, understand the connection between this and these non-trivial exponents in this intermediate regime?
Yeah, thanks, Antoine. So my take on that is this: we also see in the intermediate regime, if you study the self-consistent power laws in the self-energy, as Philip saw, we don't get 0.5, we get something like 0.8. But I convinced myself that this is not a clean power law. It seems to me it's some crossover regime, and it comes about basically because you have particle-hole asymmetry. And let me see if I can get back to the corresponding plots. And so I was not able to contact with this omega to the 1/2. So, and certainly in the conformal field theory analysis, there's no trace of this 1/2. So now again, my slides are not going forward. So the short answer is, we also see trivial power laws, but I don't think they are systematic, particularly if you don't have a broad energy window, then I think it's just some crossover.
I see. So your analysis is that this is a crossover regime that was somehow a precursor observation revealing this intermediate fixed point.
Yeah. In particular, I should say, when I say we see omega to the 0.8, this is now on the Matsubara axis. That's also only on one side of omega. So let's say for positive frequencies or for negative ones. For positive ones, there's no clean power. So due to that reason, I concluded it's not a systematic effect.
Okay, thank you very much.
Not a systematic power.
Thank you.
Okay, do we have questions locally? Yes, Vlad, please come up.
So this is my this is my question. In the beautiful work that Gabi has done some years ago, they introduced the concept of resilient quasi-particles, but that was done within the single-site DMFT of the Dopp-Haber model. And so above the Fermi liquid regime, there is a regime of linear resistivity, which and far below the scale where the quasi-particles completely disappear. But my understanding is that in this case, the impurity model did not have any non-Fermi liquid fixed point, non-trivial non-Fermi liquid fixed points, but it was a result of self-consistency. Now my question is, this physics that is described here is motivated by Hund's metals, for example, and we often see a Fermi liquid regime which is modest, and then there's a broad regime with linear resistivity. So my question is it possible that in these many Hund's metals, this linear resistivity regime is a result of basically self-consistency and not a result of these non-Fermi liquid fixed points of the impurity model?
So I don't have a definite answer to that, but I would find it plausible what you are saying, because this non-Fermi liquid fixed point that we analyzed here, let's say you have to work hard to dig it out, right? You have to take the Anderson self-consistent Anderson model, relinquish self-consistency, then map it to the three-orbital Condor model, and this Condor model, then you have to tune one of its parameters in an unphysical way. So while I think it's plausible to say there is a non-Fermi liquid fixed point in the background somewhere, right? I think it's so far in the background that I don't see a direct route from there to, let's say, linear in T resistivity. So that would be my take on that. It would be interesting to hear what Gabi has to say to that.
Well, Gabi, do you want to say something? Up here. Okay, so no comment for right now. We don't have anything locally in the room. Is there anything online? If there are no further questions,
I don't see anything.
All right. So if there are no further questions from online, let's thank Jan again.
So I just have one comment.